Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 5, in which I will discuss some problems on GCD, greatest common divisor. Now we solve problem number 1. If GCD of A and 4 is 2 and GCD of B and 4 is 2, then GCD of A plus B and 4 is 4. Now we solve this. Given that GCD of A and 4 is 2, implies that 2 divides A, implies that A equal to 2m. M is an integer. This is number 1. Again, given that GCD of B and 4 is 2, implies that 2 divides B, implies that B equal to 2n, n is an integer. This is number 2. Now, GCD of A and 4 is 2 here, and we use number 1. A equal to 2m implies that A equal to 2m and here 4. GCD of 2m and 4 equal to here 2. This means m is an odd integer. If we take m is an even integer, then m equal to 2k, k belongs to z, and in this case 2m and 4, GCD of 2m and 4 will be equal to, in place of 2m we write 2k and 4, GCD of 2 multiplied by 2k and 4 equal to, we may take 4 outside and GCD of k, and here remains 1, and GCD of k and 1 is 1, and this equal to 4, which contradicts with this concept. Therefore, m is not an even integer. That is, m is an odd integer. This is number 3. Again, since GCD of B and 4 equal to 2, and we put the value of B equal to 2n, similar to above case, n is an odd integer. This is number 4. From 3 and 4, we get m plus n is an even integer. Since odd integer plus odd integer is an even integer, m is an odd integer and n is an odd integer, their sum is an even integer. Implies that m plus n equal to 2c. C belongs to Z. This is the symbol for even integer. This is number 5. Now, a plus b equal to a is 2m and b is 2n equal to 2m plus n equal to 2 using 5, m plus n equal to 2c equal to 4c. This is number 6. Now, GCD of a plus b and 4 equal to a plus b means 4c and 4. GCD of 4c and 4. We may take 4 outside. Here remains c, here 1. Since GCD of c and 1 is 1, this is equal to 4. Therefore, GCD of a plus b and 4 equal to 4. Proved. Now we solve problem number 2. Here it has been stated that the fraction a by b is said to be in lowest term if GCD of a and b is 1. Now, this is the part of the problem. Let a by b and c by d be fractions in lowest terms. If their sum is an integer, then prove that modulus of b equal to modulus of d. Since given that a by b and c by d are in lowest term, therefore GCD of a and b equal to 1 and GCD of c and d equal to 1. This is number 1, this is number 2. Now, given that their sum is an integer, let a by b plus c by d equal to m is an integer. Implies that bd, here ad plus bc equal to m. Implies that ad plus bc equal to MBD. Implies that AD equal to MBD minus BC. This equal to, we may take common B, MD minus C. Here we see that AD equal to B multiply MD minus C. MD minus C is an integer. Therefore, B divides AD. Since MD minus C is an integer. Here we see that GCD of A and B is 1. Therefore, from this we get that B divides D. Since GCD of A and B equal to 1. This is number 4. From 3 we get BC equal to MBD minus AD. This equal to DMB minus A. Here M, B, A all are integers. Therefore, MB minus A is an integer. D multiply an integer equal to BC implies that D divides BC. Since MB minus A belongs to Z. Since GCD of C and D equal to 1, therefore D divides B. Since GCD of CD equal to 1. This is number 5. From 4 and 5 we get here B divides D, here D divides B. Therefore, from 4 and 5 we get B equal to plus minus D implies that modulus of B equal to modulus of D. Proved. Now we solve problem number 3. Prove that GCD of A and A plus K divides K for all integers not both 0. Now we solve this. If both integers are 0, then here we get GCD of 0 and 0 divides 0. Means 0 divides 0. And which is an absurd concept. Now we prove for all integers not both 0 case. Let GCD of A and A plus K equal to D implies that D divides A and D divides A plus K. This is number 1 and this is number 2. From 1 and 2 we get D divides A plus K minus A from the concept of divisibility. Implies that D divides K and D is the GCD of A and A plus K divides K. Proved. Now we solve problem number 4. Prove that GCD of A and A plus 2 is 1 or 2 for every integer A. Now we solve this. Let GCD of A and A plus 2 equal to D implies that D divides A and D divides A plus 2. This is number 1, this is number 2. From the concept of divisibility, we know that if D divides A and D divides A plus 2, then D divides A plus 2 minus A implies that D divides 2. Since only two integers 1 or 2 divides 2, therefore D equal to 1 or 2. Proved. Now we solve problem number 5. Let S and G greater than 0, be given integers. Prove that integers x and y satisfying x plus y equal to s and GCD of x and y equal to g if and only if g divides s. Since given that x plus y equal to s and GCD of x and y equal to g implies that g divides x, implies that x equal to gm and g divides y, implies that y equal to gn. Here m belongs to z and n belongs to z. This is number 1, this is number 2. Therefore from 1 and 2 we get x plus y equal to gm plus gn, implies that x plus y equal to s and here g common, m plus n. Since m and n are integers, therefore m plus n is also an integer. That means by divisibility concept, g divides s. Proved. Conversely, let g divides s implies that s equal to pg, p belongs to z. Let this is number 3. Let q and r are integers such that q plus r equal to p and GCD of q and r equal to 1. Let this is number 4 and this is number 5. Using 4 in theory, s equal to q plus r multiply g. This equal to qg plus rg and this equal to qg equal to let x and rg equal to y. Let qg equal to x and rg equal to y. This is number 6. Now GCD of x and y equal to x means qg, y means rg. Here we may take g outside, GCD of q and r. Here in 5 GCD of q and r is 1. This is equal to g multiply 1 equal to g. Therefore we get s equal to x plus y and GCD of x and y equal to G. Proved. Now we solve problem number 6. Let B and G such that G greater than 0 be given integers. Prove that equations GCD of x and y equal to G and x multiplied by y equal to B can be solved simultaneously if and only if G square divides B. Now we solve this solution. Since given that B and G greater than 0 be two integers, and also given that GCD of x and y equal to G, this is number 1, and x multiply by y equal to B, this is number 2. From 1 we get G divides x and G divides y, implies that x equal to mg and y equal to ng. M and n are integers. This is number 3 and this is number 4. From 3 and 4 we get x multiplied by y equal to m n g square. Since m and n are integers, therefore their product is an integer. M n is an integer, implies that xy equal to b equal to mn multiply g square. From divisibility relation we know this means g square divides b. Proved. Conversely, let g square divides b, implies that b equal to p g square. P belongs to z. Let this is number 5. Let q and r be two integers such that p equal to qr and GCD of q and r equal to 1. This is number 6 and this is number 7. Therefore, from 5 b equal to p means qr g square. This equal to qg multiply rg. Let qg equal to x and rg equal to y. Let qg equal to x and rg equal to y. Implies that b equal to xy. This is number 8. Now GCD of x and y. X is qg and y is rg. We may take g outside and GCD of Q and R. GCD of Q and R is 1 in 7. This equal to G multiply 1 equal to G. This is number 9. Therefore, from 8 and 9 we get B equal to XY and GCD of XY equal to G. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.